Hello and welcome. In this video, we'll be reviewing a brief introduction to the convolutional neural network model. Convolutional neural networks, or CNNs, have gained a lot of attention in the machine learning community over the last few years. This is due to the wide range of applications where CNNs excel, such as object detection and speech recognition. In a later part of this video, we'll examine the object recognition problem, which is a key consideration when using CNNs. You'll also get an idea of how a CNN structure allows it to extract the elements from an image. For example, you'll see how a CNN learns to pick out a person or a dog or even chairs from an image, even if the chairs are only partially visible. Indeed, this is not an easy task for computers, and it took years of dedicated research to achieve this. The original goal of the CNN was to form the best possible representation of our visual world in order to support recognition tasks. The CNN solution needed to have two key features to make it viable. First, it needed to be able to detect the objects in the image and place them into the appropriate category. And second, it also needed to be robust against differences in pose, scale, illumination, conformation, and clutter. The importance of this second feature simply cannot be overstated, since this was historically a huge limitation of hand-coded algorithms. Interestingly enough, the solution to the object recognition issue was inspired by examining the way our own visual cortex operates. In short, the CNN starts with an input image. It then extracts a few primitive features and combines those features to form certain parts of the object. And finally, it pulls together all of the various parts to form the object itself. In essence, it is a hierarchical way of seeing objects. That is, in the first layer, very simple features are detected. Then, these are combined to shape more complicated features in the second layer, and so on, to detect things like a cat or a dog or any other object we're needing to detect. The convolutional neural network was developed from this sequence of steps. Let's consider the building in the lower right-hand corner of this image. How can a trained CNN learn and recognize that it's an image of a building, rather than some of the other elements that are situated in the photograph, such as a person or even those clouds in the sky? Well, in the training phase, CNNs would receive many building images as input. Then, CNNs will automatically find that the best primitive features for a building would be things like horizontal and vertical lines. Much like the neurons firing in a person's visual cortex, the first layer in a CNN reacts, so to speak, when it receives an image that has horizontal or vertical lines. Once these simpler features, such as lines, are combined, CNNs learn to form higher abstract components, like the windows of the building and the building's external shape. It can then use these basic parts to form the complete object and learn how the entire building essentially looks like. Later, if it sees an image of a building that it hasn't seen before, CNNs can make a decision if the new input image is of a building based on the persistence of the various features it has stored. It is the same process for learning and detecting other objects, such as faces, animals, cars, and so on. So, as you can see, the CNN is a set of layers, with each of them being responsible to detect a set of feature sets. And these features are going to be more abstract as it goes further into examining the next layer. So, at this point, you should have a basic understanding of the principles behind a convolutional neural network and how CNNs might be used in an application. Thanks for watching. In this video, we'll explain how CNN can solve an image classification problem such as digit recognition. First, let's see why traditional shallow neural networks do not work as well as CNN. As mentioned before, one of the important steps in the modeling for classification with shallow neural networks is the feature extraction step. These chosen features could simply be the color, object edges, pixel location, or countless other features that could be extracted from the images. Of course, the better and more effective the feature sets you find, the more accurate and efficient the image classification you can obtain. However, as you can imagine, the process of selecting the best features is tremendously time-consuming and is often ineffective. Also, extending the features to other types of images becomes an even greater problem. Convolutional neural networks, or CNNs, try to solve this problem by using more hidden layers, and also with more specific layers. So, when using CNN, instead of you choosing image features to classify dogs versus cats, for instance, CNNs can automatically find those features and classify the images for you. Instead of using a dogs and cats dataset, though, let's use a more practical example here. The MNIST dataset is a database of handwritten digits that has a training set of 60,000 examples. The great thing about the MNIST dataset is that the digits have been size normalized and centered in a fixed size image. Now, consider the digit recognition problem. We would like to classify images of handwritten numbers where the observations are the intensity of the pixels, and the target will be a digit from 0 to 9. So, our objective here is to build a digit recognition system using CNN. Now let's look at it from a higher level. Basically, if we look at the pipeline of our deep learning process, we can see the following phases. First, pre-processing of input data. Second, training the deep learning model. And third, inference and deployment of the model. In the first part, we have to convert the images to a readable and proper format for our network. Then, an untrained network is fed with a big data set of the images in the training phase, so as to allow the network to learn. That is, we build a CNN and train it with many handwritten images in the training set. Finally, we use the train model in the inference phase, which classifies a new image by inferring its similarity to the trained model. So, this model can be deployed and used as a digit recognition model for unseen cases. Now, let's focus on the training process. As mentioned before, a deep neural network not only has multiple hidden layers, the type of layers and their connectivity also is different from a shallow neural network, in that it usually has multiple convolutional layers, pooling layers, as well as fully connected layers. The convolutional layer applies a convolution operation to the input and passes the result to the next layer. The pooling layer combines the outputs of a cluster of neurons in the previous layer into a single neuron in the next layer. And then, the fully connected layers connect every neuron in the previous layer to every neuron in the next layer. In the next video, you will learn more about these layers and their specifications in detail. Thanks for watching.